Good evening, everyone. Welcome to the public lecture hosted by KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology. My name is Xinan Du. I am the Outreach Engagement Manager at KIPAC, and I will also be your main host for tonight. It's very exciting to see all of you joining us here in person, especially for our first lecture in 2025. And we also welcome the online audience who is watching the live stream right now. For tonight's talk is going to be focused on a very interesting interdisciplinary area that combines computer sciences and astronomy. And we're also very excited to share with you how some of the technological advances that we see and use in everyday life can also help us do so much more in scientific research. Before we start, I would like to just give a quick shout out to the entire team who has been supporting this event behind the scene. These include the front desk staff, some of those checked you in, also our AV team here, and also Leon, who is helping me with live stream. Since this is a hybrid lecture, we also have chat moderators online who are subject matter experts, very knowledgeable on this topic that help answer questions from the online audience as they come in. So I will give them a chance to say a quick hello to everybody. All right, so first we have Sucheta.
Hi, everyone. I'm Sucheta Kure. I'm a postdoctoral researcher at KIPAC. I study galaxies, how they form and how they evolve. Machine learning and AI is a big part of my research. So I'm happy to be involved in the discussion today. Thanks.
Thank you. And next we have Joe.
Hi, everyone. Very nice to meet you online. My name is Joanna Chuka, but people call me Joe. I'm a research scientist at KIPAC. My main research is in galactic archaeology, so I just generally deeply care about the Milky Way. And I also really care about AI as well and AI-human collaboration. And today I'm equally excited to hear about Dalya's amazing talk. Thank you so much.
Wonderful. And last but not least, we have Philip.
Hi, everyone. My name is Philip Frank. I'm also a postdoc at KIPAC. Primarily interested in our own galaxy, the Milky Way as well, and very much a huge fan of machine learning and AI as a tool to advance science and astronomy in particular.
Great, thank you all. And so for all of you who's joining us online, you can use the chat box on the right-hand side to put in any questions that you want an answer for. And we also encourage you to engage in discussions. Most of the questions will be answered directly by the chat moderators as they come in, and we'll save a few for Dalya to answer during the Q&A at the very end. And for all of you joining us in person today, please save your questions until the Q&A. And Dalya will also be here after the event if you want to chat one-on-one. So Dalya is not getting out of this room until all the questions are answered, okay? All right, so now it's my greatest pleasure to introduce tonight's speaker, Dr. Dalya Baron. Dalya is a research scientist here at Stanford who focuses on the intersection of AI and astronomy. So as an astronomer, she uses different telescopes to study very distant galaxies, and including the stars and gas inside of them, and also across the electromagnetic spectrum. She's also specifically interested in machine-assisted discovery and has developed and used machine learning algorithms to identify and uncover unknown trends and also novel phenomena in those large public astronomical data sets. Dalya has also been very enthusiastic about science education. So growing up as the only female student in her physics class, Dalya hopes to serve as a role model and inspire more students in physics, astronomy, and STEM in general. So without further ado, let's welcome Dalya.
Okay, hello everyone, good evening. I'm extremely excited to see all of you here. And I'm happy to tell you a bit about this newly evolving field within astronomy. We're experiencing really a technological revolution that is driven by the development of these artificial intelligence algorithms. And I'm happy to tell you today about how this revolution actually reshapes the way we study the universe and make discoveries. So we don't really need to follow the news so much to know that something exciting is going on. Living here in the Bay Area, we just need to sort of lift our heads and see all the ads and billboards everywhere. We see artificial intelligence everywhere. And indeed, it has affected and changed a lot of different disciplines and industries. I'm listing here just a couple of examples. So in healthcare, for example, artificial intelligence is already integrated in the decision-making process and helps monitor different signs, for example, from smartwatches and things like this, help decipher images of the human body. If you are driving in San Francisco, you will see these self-driving cars, Waymo, which rely on algorithms of artificial intelligence to make different decisions to allow them to navigate in the city of San Francisco. And of course, we have also heard about the development of large language models, ChatGPT, Gemini, Claude, where we can go onto a web browser and chat with these large language models about any topic we'd like and in any language that we'd like as well. So as this revolution is unfolding, we first want to understand what is artificial intelligence, what is machine learning, and how it's all connected to basic programming. So first, let's start with what is a program. A program takes something as an input. It can be an image, it can be voice, it can be text, it can be numbers, and it has a certain output. In traditional programs, programmers implement a number of explicit rules of how input translates into output. If a number is larger than 3, the output will be yes. If the number is smaller than 3, the output will be no, for example. So this is how traditional programs work. And machine learning are a type of programs where the computer learns the rules via training from examples of input and output. So in this case, we do not provide explicit rules that map the input to the output, but in fact, the computer itself learns these rules by seeing many examples of input and output. Artificial intelligence is a sort of generalization of that, where computers are used to do tasks that are usually done by humans, such as understanding languages, recognizing images, and making complex decisions. And the reason why I call it a generalization is because all of these tasks that humans do rely on a very complicated set of rules. When we recognize an image or recognize a certain language and read a book, we have a very complicated set of rules that we follow in order to convert it into some output. And so this is what we call artificial intelligence. And as these change different disciplines, we sort of need to understand what happened in astronomy over the past couple of decades. So astronomy, compared to other physical and natural sciences, we cannot build controlled experiments. Unfortunately, I cannot build an experiment in the laboratory where I study how planets form. The mass and the scale is too large for me to be able to fit it inside the laboratory. But we use the fact that the entire universe is essentially an ongoing experiment with countless of different experiments that are taking place all of the time. Stars, planets, galaxies, every individual object in the night sky is essentially an ongoing experiment, and we can observe this in order to derive the physical laws of nature. And so what we're doing is building these surveys and telescopes to map the night sky to constrain physics, chemistry, and biology. And in fact, we have been extremely productive in doing that. We have these very large surveys that map the night sky and have been providing millions and billions of observations of astronomical sources. We have observed galaxies, both in images and in spectroscopy, where we measure flux as a function of wavelength. We have observed stars. We have observed how brightness of astronomical objects changes as a function of time from night to night. So we're talking about an exponential increase in the number of observed sources. But in addition to that, one thing that I find particularly exciting is the fact that astronomical objects today are being mapped by different instruments across the electromagnetic spectrum. And all of these different images give us different snapshots or different points of view of the same astronomical sources. So what you're seeing here, that's the Andromeda galaxy as seen by different wavelengths. From the lowest energy radio wavelengths that you're seeing on the left, all the way to the highest energy X-ray emission that you're seeing here on the right. And each of these images traces different components of the galaxies that trace different physics that are at play. So on the left-hand side, all of the left images here involve physics at low energy. So for example, molecules and atoms that are excited by the radiation of stars around them and emit in these wavelengths. And as we move all the way to ultraviolet and X-ray, we're looking at high energy physics of high temperatures, high energies that emit what we're seeing here. And so we have an exponential increase in the number of sources, but also the complexity of information increases. And this leads to a challenge as well as an opportunity, because now we can start understanding physics across multi-scales and across different energies at the same time. And one of the tools with which we have tackled these large and complex data sets is machine learning and artificial intelligence. And in this lecture, I'm going to sort of review the evolution of using these tools within astronomy. So we'll start with 2000 to 2015 roughly, where we have used traditional machine learning algorithms where what these algorithms essentially do, they employ a relatively simple set of rules on the different features that they're seeing. And these algorithms required us to define the aspects of the data that are important for the task at hand. I will explain in a second what exactly it means. And in addition to that, they required us to label the data, to provide ground truth. And so because of these requirements, the application of these tools to astronomical datasets was actually limited to a number of specific cases and was not widely used. But one example of a field where machine learning has made a huge impact is in the field of identification of how brightness of astronomical objects changes with time. So what you're seeing here is an image of M101, a spiral galaxy quite nearby. And the image was taken in April 2023. This is an image of the same galaxy taken in May 2023. And perhaps you can see here. You can see here. Let's do like this. Oh. Okay. So perhaps you can see here that a new point, a bluer new point appeared in the right-hand side image. What happened in this galaxy is that a massive star exploded, emitting a lot of radiation that is actually changing the brightness that we're seeing in this particular spot in the galaxy. And so there are various objects in the universe that have their brightness change as a function of time. And each of these trace different physical processes in the objects that we're looking at. So we know of different types of variable stars whose brightness changes as a function of time, sometimes periodically, sometimes not periodically. Massive stars at the end of their evolution explode and produce vast amount of radiation that is seen as point sources within galaxies. In addition to that, galaxies host supermassive black holes in their center. And these supermassive black holes sometimes accrete matter through an accretion disk of gas and dust. And this gas gets heated quite significantly and emits radiation throughout the electromagnetic spectrum that also varies in a quite chaotic manner as a function of time. And so we're interested in finding these sources whose brightness changes. And so how do we do that? Astronomers have been developing what we call transient identification factories, where transient is an object whose brightness changes as a function of time. And the way we do that, we have these robotic telescopes that take images of the same region in the sky night after night, monitoring these regions and looking for places where the brightness has varied. The way we actually do that, we have an image that has been taken of the source at some previous time, which we call the reference image. And every night that we look at the same region in the sky, we take what is called the science image. So if we want to see whether something changed in brightness between the two nights that we're observing, we're subtracting the reference image from the science image, leading to what we call the difference image. And if something changed in the galaxy during the time between the observations, we will see it as a bright point in the image. And so this is the basic way in which we identify transients in images. The challenge is that although some of these variations are real and so associated with real physical phenomena taking place in these objects that we observe, we also have variations that are due to things that we find less interesting, like the weather that affects the atmosphere conditions that will affect the size of the emitting regions that we're going to see in the images. Essentially, the atmosphere blurs the light that we're seeing from distant objects, making objects appear larger or smaller. And so if the weather changed between different nights of observations, the sizes of the object will change, and then we will have some residual emission in the difference images. Astronomers usually call the real events real, and those events we call bogus. And so the question is, how can we separate the real from bogus events? And so astronomers that work in this field can actually look at these data sets and make a decision in a matter of a couple of minutes of whether the object is real or bogus. The challenge is that even 20 years ago, we had thousands of such events per night. And so exploring these images manually as astronomers is not something we can do night after night for a couple of years of survey lifetime. And so we need to be able to do it automatically. And this is where machine learning has really made a huge impact. One of the first huge impacts that machine learning made in astronomy was in that field, where machine learning algorithms have been trained to separate between real and bogus events. So the way we do that, we have these difference images, and then we need to define which aspects of the data are important for the classification task. So in this particular case, this will be things like the size and the shape of the emitting region, how many emitting sources we have in the difference imaging, and what are the weather conditions, for example. And in order to train these algorithms, we need to provide labels. We need to build a training sample where we know the measured features and we know the outcome. We know whether they are real or bogus. And so astronomers have been building such training samples, but even just the training samples are too large for astronomers to do on their own. And they have been collaborating with what we call citizen scientists. These are members from the public that help astronomers in classifying astronomical events, either transients, as you see here, or shapes of galaxies, or how brightness of stars changes as a function of time. And there are huge projects where the public is actually involved in building these training data sets by providing the classifications that we need for the sources. So one such example is Zooniverse, which includes several different projects of classification, and you can actually look it up online and help us classify sources, which will later help us build automated models to do these tasks. Now, what I've been telling you up until now was a summary of what happened in the transient astronomy field over the past 20 years. And the near future is extremely exciting. The Vera Rubin Observatory is going to start producing alerts in this summer, and it's going to produce around 10 million alerts per night. This is extremely exciting to talk about it here at Stanford, because Stanford and KIPAC have been extremely involved in the Vera Rubin Observatory, and actually the camera that is used to monitor the night sky and produce these alerts has been built here at SLAC. So we're moving from thousands of events per night to millions and tens of millions of events per night. So we need to make sure that these tools can both be fast and reliable and robust in order to identify the real events versus the bogus ones. So this is essentially the traditional machine learning part of the history. And around 2015, we started using deep neural networks in our scientific exploration. The main difference between traditional machine learning algorithms and deep neural networks is the fact that these deep neural networks can identify on their own which aspects of the data are important for the task at hand. So we no longer need to define it ourselves, and this opens up a possibility to do it in fields where we do not necessarily know the features that are important in advance. They still, in most of these cases, required labels. So a brief explanation of what a neural network is. A neural network is a system of connected neurons. Each of these neurons is a circle that you're seeing here in the diagram, and these neurons are connected to each other. They have input, they have output, they move information from the beginning of the network to the end, and they can be activated given certain inputs. And this entire structure is actually inspired by the human brain. And the way these algorithms are trained is that we have some input data coming in the input layer. We take this input data and we break it up to tiny little boxes, and every box goes to a given neuron. And all of the neurons are connected to all of the other neurons. So you can see that information flows in a very complex manner from every neuron to every other neuron. At the output, again, we need to define labels. So in this particular example, my label can be a flag of whether there is a dog in the image or there is a cat in the image. And we still need to construct training samples where we have images on the one hand, but on the other hand, these labels, these cats and dogs, and we train these neural networks where we basically, what we learn during the training are these connections between the neurons. So every line that you're seeing in the diagram connecting a neuron to another neuron is something that the neural network learns. So you can see that now it has to learn a much larger set of rules of how to convert input to the output that you're seeing here. But it turns out that this process is extremely useful in identifying textures and shapes within datasets, and basically allow us to identify the features that are important for what we want to do. One example of where machine learning with deep neural network has advanced astronomy is in tracing how galaxy shapes change across cosmic time. So we have billions of images of galaxies. And a very interesting property of astronomical objects is because the speed of light is finite and constant, it means that it takes some time for light to reach us from an emitting source. And so if I have a galaxy and it is farther away from me, the light that is emitted by this galaxy, it will take it longer to reach my telescope. And so as a galaxy is farther away from me, I'm actually seeing it as it was when the universe was younger. The universe now, we believe, is 13.7 billion years old. And so as we look at galaxies that are farther away, we're doing a bit of an archaeology. We're seeing what the universe looked like when it was younger. And so we can ask the question, given all of these billions of galaxies, how does their shape evolve as a function of cosmic time? And here is an image showing how what galaxies look like, at least when they're close enough to discern different features. You can see that their shape differs, their colors differ from one galaxy to the next. And again, in this particular case, we have used deep learning algorithms in order to learn what is the shape of galaxies and to study how it changes. So what you're seeing here is an example of a class of galaxies called elliptical galaxies. You can see that they're sort of all the same. They look like these ellipsoids, basically. These are very massive galaxies that form little stars. They have little gas and dust in them. Another class of galaxies, for example, are what we call spiral galaxies, specifically unbarred spiral galaxies. And you can see that these galaxies have spiral arms. Most of the star formation that happens in these galaxies actually happens along these spiral arms that are also very rich in gas and dust. Another type of galaxy are what we call barred spiral galaxies, where you can sort of see from the center of the galaxy, you can see two bars extending from the center, and only from there you start seeing the spiral arms of the system. And so we can take datasets such as these and learn the shapes of galaxies. And for that, again, we need to define the labels. Elliptical galaxies, spiral galaxies, barred spiral galaxies. But now we no longer need to define what features of the data are most important, because the deep neural networks can learn it by themselves, but they do require much larger training samples in order to do that. And here as well, citizen scientists have helped tremendously in building these training samples for astronomers. And once these networks are trained, we can take them and apply them to the billion images of galaxies that we have. And we see an evolution of galaxy shape as the universe becomes older and older. If we look at the very young early universe, we will see that galaxies have irregular shaped structures with very chaotic star formation rate that rises and goes down all of the time. And as we move further and further to present days, we start seeing at what epoch spiral arms have started to form, when galaxies became these rotating structures that we're seeing here in the middle panel. And as time evolves further, we're starting to see more and more of these elliptical galaxies that turn off their star formation. So we can essentially see how this shape, together with how galaxies form stars, changes in a continuous manner as we move from the very early universe to present days. So this is the part about deep neural networks. Since 2020, roughly, we have seen the development of a generalization of this deep neural network called foundation models, which are based on deep neural networks, but they are often more, they're larger in scale. And an interesting aspect of them is that they can handle different types of data. So what I showed you up until now was imaging data, where I have only images. But as I told you in the beginning, in astronomy, we have images, we have spectra, we have brightness as a function of time. And so these new models can actually handle all of this information at the same time, which makes them very powerful. The second thing that is very exciting is that these new models do not necessarily need labels in order to train. They learn on the data, but what they're trained to do is reproduce the data itself. And so if we are not limited by the requirement of having labels, we can start applying these models to learn any type of astronomical dataset. And at the basis of these tools are what we call a structure of an autoencoder. This is also a type of neural network. You can see here the circles are these neurons, and they're again connected to each other, moving information around. But the structure of the network looks different from the one I showed you before. So we have the input layer as we had before, where we break the data into little pieces that go into these neurons. But then you can see that the number of neurons, as we move to the center, decreases. What we're essentially doing, we're compressing the information. We're starting from a large number of neurons that describe all of these different pixels in the image, and we decrease this number and compress the information into a smaller and smaller set. Once the information is constrained into this smaller set that is called the latent space or the encoded data, we decode it back up. And the final layer of the network is actually of the same size as the one we started with, where the output that we want to have there is the input that we started with. And so these type of networks are trained to be able to reproduce the input data, but we tricked them. We made them compress the data first. So from a very large representation of the dataset, we're moving to a very compressed one and sort of make these networks learn a compressed version and how to then build the entire object from this compressed version. And these types of algorithms are now being used to do very exciting things in astronomy. One example is actually simulating the universe with artificial intelligence. So I've told you that we cannot build controlled experiments on Earth. We can either observe the night sky and see the experiments that the universe gave us, or alternatively, we can build computer simulations that try to mimic as best as possible the physics that we believe governs the universe. And so there is an entire field of simulating how galaxies evolve inside an evolving universe, where you start with some initial conditions and a number of particles in the early universe, and you implement different physics laws that we believe take place, like gravity, hydrodynamics, magnetism. We implement them within these simulations and let the simulation run to see what type of structures evolve. And these called cosmological simulations because we start from a very large volume of particles, which slowly start being concentrated in specific regions in space where galaxies form, star formation happens, and all the interesting physics that we're seeing here. I'll show you an example of a simulation like this. What you're seeing here is how structure forms. The mass is roughly seen in purple, where you see these filaments of mass, where basically particles are attracted due to gravity into specific regions in the space. And in the regions that are densest, this is where galaxies form. And once galaxies start forming and stars begin forming, we see them hitting the surrounding medium around them in these pink colors that you're seeing here. So every such knot that you're seeing in the cosmic web is a region where massive galaxies form and hit the surrounding medium around us. Now, these simulations are extremely large scale. The biggest simulations are actually, the biggest simulations can run for months or even years to produce these detailed images of what the universe looks like. And even then, we're limited by the resolution that we can have in the simulation, which means that not all physical laws and interactions are actually explicitly modeled within the simulation. Some of the physics that happen take place on a scale much smaller than the scale that we can see in our simulation. And so in these cases, we employ sort of approximations, what we think would be the effect on large scale of these changes on small scale physics. For example, how atoms react and how chemistry forms molecules and dust particles within the gas in the galaxies. So things like this, we obviously cannot implement in these simulations, and we sort of need to build formalisms to approximate them. But even then, these simulations take months. And often we have different uncertainties regarding how to approximate different physics. And it is difficult to explore different choices for these uncertainties. And these new type of foundation models and deep neural networks have actually been extremely useful in training on simulation data, starting from initial conditions and moving as a function of time, and sort of giving us a way to emulate simulations, but at a much faster pace. So this is something that is being studied right now in the present. The second extremely exciting thing that we can do with these new types of models that no longer require labels is identification of unknown unknowns. So how can we divide the objects in our samples into groups? Most of the objects are what I would call known knowns. These are the normal, boring galaxies that we see that comprise more than 90% of the galaxies that we see in imaging data. We think that we understand some of the physics that drives them and evolves them as a function of time. In addition to them, we have what I call the known unknowns. So these are anomalous objects within our datasets that have some unusual properties that we have already identified. So we are aware of the existence of these unusual types of systems in our surveys, and we know how to look for them. We can use, for example, traditional machine learning algorithms to look for these sources, build a group, and then try and study it to understand what happens. The interesting question is how to define unknown unknowns. So within our datasets are objects which we don't know that exist there. And these are the most interesting objects. These are the objects we want to find, but we don't know how to define them. We don't know what they are. And so the question is, how can we find these objects in an automated way? And it turns out that these new types of models are actually extremely useful in finding such objects. So essentially, because they don't require labels and they are trained on the data to reproduce the data itself, they learn what is considered to be normal. And from there, we can understand what is considered to be not normal or anomalous and identify these sources. And so here you can see an example of images of sources that have been identified as anomalous, and you can see that they are very different from the galaxies I showed you before. Some of these are actually merging galaxies that merge one into the other. Others are strong gravitational lenses. So essentially, we have this time period here where we moved from traditional machine learning to deep neural networks and now using foundation models. Where are we going from here? So we have seen the development of these large language models in computer science, and we believe that this has a potential to create actually a collaboration between humans and AI agents to push forward scientific discovery. So these large language models today are already able to summarize large bodies of literature. They're able to tune themselves to a specific expertise. I can tune an AI large language model to be an expert in instrument construction, for example, or to be an expert in magnetism. These models can also interact and analyze data, and they can actually interface with other tools and algorithms as well. And so an interesting question is whether these new models can be integrated into the discovery process, not as tools, but as agents, as part of the scientific process. So can we use them to generate the next hypothesis we want to test as scientists? Can we use them to design the next generation of surveys and instruments to answer these questions? Can they provide peer review and provide scientific criticism to the work that we're doing? So these are the type of questions that we're trying to think about right now. And as with every field where large language models have been used, one thing that sort of changed dramatically from these traditional methods to the methods that we're seeing here is the complexity of the decision process, the number of rules that move you from input to output. And these models are now so large that it is very often challenging to understand exactly what they learned. And if we don't understand the scientists what they learned, we are not sure whether we can trust their outputs. So there are big questions about transparency and trustworthiness that we're now engaging in the discussions of how can we make these tools robust enough to be an integral part of the scientific exploration process. The last thing I want to mention is I'm a part of the Center for Decoding the Universe. This is a new collaboration between KIPAC and Stanford Data Science. And our goal is to answer the biggest questions about the universe using data science and AI techniques. In particular, we want to understand what the universe is made of. So what's the nature of dark matter and dark energy? We want to understand how does the universe work? So what physics drives the astronomical objects that we're seeing? And we want to understand, where do we live? So what is the structure of the Milky Way, and how stars, planets, and eventually life formed within it? And you can go to this QR code here. We had a quarterly forum a couple of months ago where we defined these questions, and every session has a starting talk that defines these questions in quite an accessible way. So I encourage you to go and see what exactly it is that we're interested as astronomers to be able to solve. And so how do we plan to answer these questions? The first thing is that we want to use the advancements in AI and machine learning to solve problems that were previously too difficult to solve. One such example that we've identified is the inference of the three-dimensional structure of astronomical objects. So everything we see, everything we observe in astronomy is a two-dimensional projection of a three-dimensional object. And we believe that with the tools that are available today, we can make the step forward of inferring the structure of the three-dimensional sources that emit the radiation. We're also interested in using the state-of-the-art data science tools to mine astronomical data sets. So all of these complex data sets that observe objects across the electromagnetic spectrum, where we want to combine everything that we have observed, specifically about galaxies and their gas and stars, into a single inference model, where we can look for anomalous objects, small groups of interesting objects, and look for new unknown trends. In addition to this, we want to build a virtual astronomical laboratory and start exploring the question of whether AI can be integrated as agents within the astronomical discovery process. We had another quarterly forum about that at the end of January. That's the link to the forum. The lectures are still not uploaded, but I believe that in a couple of days they will be. So if you're interested, you can check it out. And the important thing to note is that interdisciplinarity is the key in this particular type of endeavor. We can no longer do this only as astronomers. We need to collaborate with computer scientists, with statisticians, with people from biology and chemistry and health sciences in order to be able to solve these problems using these new tools. What I'm showing you here is just a number of the people that are involved in the center from within KIPAC. You can see the full team in the QR code here. We have a lot of collaborators from different disciplines and fields across Stanford. But these are some of the people that are involved within the Center for Decoding the Universe, where I particularly wanted to give a shout out to the junior people. So these are all the ones that are marked with purple colors that have been working tirelessly in building this new center, defining these projects, understanding what this center is going to be about. So this is mostly thanks to these people that have been doing the work. So to summarize, I want to sort of summarize what we've talked about during this lecture and how machine learning and AI has been evolving within astronomy to help us do our science better. In the 2000 to 2015, we mostly used machine learning to do an automatic identification of objects given a set of features and labels. We had to define a lot of the things that we care about, and so it limited our applications to quite a small range of questions within astronomy. We then moved to using deep neural networks to learn the shapes, textures, and complex relations between the objects in our datasets, but we still had to provide labels to do that in most of the cases. We then moved to foundation models and unsupervised deep neural networks, where we no longer require having labels. And these new networks are able to emulate complex simulations of our universe, as well as help us finding unknown unknowns, these objects that we want to uncover in our large datasets. The future is an open question. We're not sure. One place where we're excited to explore is this collaboration between humans and AI in order to accelerate scientific discovery and move it forward. That's it. Thank you very much.
Great. Thank you, Dalya, for a very informative talk. That there was a lot of information packed in there. So I know all of us might just take a minute to digest a little bit. But now we'll start the Q&A session. And for any in-person questions, I will also repeat that so our online audience can also hear. Yeah, any burning questions to get us started? Over there.
Yeah, thanks for the lecture. I was curious, how the learning process changed now? Like, probably maybe it was new, starting on the field. Different for them, maybe 20 years ago. Because of AI, are they able to learn faster or have to learn differently to be able to contribute to the field as a researcher?
Oh yeah, okay. So the question was, how has AI really changed the learning process as someone getting into a scientific field, right? Whether you have seen any changes, like personally or just in general.
That's an excellent question. And we sort of see, I think that most of the changes that I've seen occurred in the past year or two with these large language models that have appeared. Before the large language models, the only thing that I think that really changed in the learning process is the fact that you now have this extra new thing that you have to learn as a PhD student or an undergrad student in order to utilize it in your research. So as instrument construction, as you need to learn optics, you also need to learn statistics and you need to learn machine learning in order to do your research better. That has significantly changed over the past year or two, where we have tools like ChatGPT that can basically answer every question that we have. So by just looking around me, it is very difficult to still know, because you need to integrate over a long period of times to sort of understand what is going on. But I think that what is going on within astronomy also goes on outside of astronomy. So for example, it is maybe less pressing to learn very deeply how to code if you can use these large language models to code for you. So for example, one thing I've seen, and this is something that you see in industry as well, large amounts of code that you were used to writing yourself, you now use this type of tools to accelerate the way that you're writing code. Another thing that changed is the way we do literature search. So when we're writing a paper and we want to write the introduction or to understand how are our results compared to results obtained from different scientific studies, we used to look in Google and sort of look for different papers, read them and understand what's going on. Now these large language models can potentially do that for us. They can summarize what happened within a certain field over a period of time. But as some of you know, these models hallucinate. So sometimes they make up things that aren't really there. They make up references, they make up papers. But so one of the things that changed in learning is that instead of learning how to efficiently identify papers in Google, we learn how to find errors in the output of ChatGPT in order to do our research in a robust way. It does save a lot of time, but we need to be extremely careful, and understanding the limitations of these tools is an extremely important acquired skill that students today learn how to acquire, essentially. So these are the type of things that I essentially saw that are changing. The physics that we're learning, I think, in this regard, I don't see yet significant changes using these large language models.
Yeah, well, thank you. That was a very holistic and comprehensive answer. All right, so we have over there.
Yeah, a question. So you talked about, it's maybe a web question. So you talked about simulation of the universe. So when I think about that, I'm thinking, okay, you simulate the universe. Can you is any research about the generative model to see how the simulated universe could be with different models. And from those models, find out if the law of physics that we know or we don't know apply, and understanding the law of physics with this generative model.
Yeah, so the question was, for those like generative models, do you actually like assume different kind of physics and then do the different like sets of parameters, run the simulations and kind of going backwards to see if there's like anything that we didn't know? Was that question?
Yeah, I mean, figure out how the thing of physics is covered by trying to find what the universe today and moving it to different generative model of what it could be and understanding the law of physics.
Yes, this is definitely one of the ways that people in this field try to constrain the physics in the models. So there are a number of different models that are available there, where the basic physics that everyone agrees on, so for example, gravity is something that all of these models share, but some of these approximations that I was talking about, prescriptions, are things that differ between the models. Implement them in different ways. And indeed, you can see that as you run this simulation to present day, the galaxies that you get from these different simulations differ in some of these properties. And so one of the things that people in the field are doing is trying to compare the galaxies that are formed in simulations to galaxies that we observe in the real universe and try to see whether a certain choice of approximations leads to galaxies that look more similar to the galaxies we observe in the local universe. It's a very challenging process because you can change a bit your approximation or your prescription and something will change quite dramatically. And in other cases, you change things and they will not change anything at all. And given that every such change takes months to run, they are choosing their tests very carefully, but they are performing such tests. Another way to sort of constrain the physics taking place on smaller scales beneath the scale that we can see in the simulations is actually, instead of simulating a whole universe, we can simulate a specific astronomical object of interest. So we can simulate a galaxy that is disconnected to an entire universe. And then we can use a much higher resolution to study the galaxy and study the physical laws that are beneath the resolution of a cosmological simulation. We can simulate, for example, an exploding star to see what kind of radiation this explosion emits, how gas moves and then collides with gas that is in the galaxy to sort of affect the structure around this region. And then from these type of simulations, we're trying to derive better approximations for the larger scale simulations. So all of these things we are doing, and the part of emulating simulations with neural networks is, at this point at least, it is used to make these types of comparisons faster. So if you have different choices of these uncertain approximations that you're doing, and you're doing it with a whole cosmological simulation, you can maybe fill the gap with deep neural networks within these different parameters, but do it much faster than what you would have done using full cosmological simulations.
Great. And this is actually related to one of the questions online. So Dana was asking, when it comes to addressing dark energy and dark matter, which you also saw it was one of the new center's goals, can you please clarify the methodologies used with the large language models in place to understand the data? So perhaps, like not in a totally elaborated way, but like on a high level briefly.
Yes, so I'm not sure that I can answer how we're going to use large language models in order to understand dark matter and dark energy better. We're at the point where we're just starting working with large language models and trying to understand the limitations of these tools and where they can be applied in a robust way. I can say that there is a lot to be done to understand dark matter and dark energy from the data science perspective, and this is what our center is trying to do. And a lot of the large experiments that are taking place within astronomy are actually built in order to understand better dark matter and dark energy. All of these surveys of galaxies actually are done in order to record distances and locations of galaxies in order to study the large-scale structure. Let me show you here. So one of the things that dark matter and dark energy really impact is how structure is formed across our universe. These purple filaments that you're seeing here, the structures that you're seeing here are extremely affected by what we believe dark matter and dark energy is. But this is a simulation. We cannot see dark matter. We can only see baryonic matter, which is the matter that is around us here. And this is the matter that emits the radiation that we're seeing. So we use galaxies and the emission from galaxies to map the structure of the universe. The problem is that for that, we need to identify billions of galaxies and precisely understand their distances from us. So once we're doing something like this, we start building this 3D structure of what the matter distribution in the universe looks like. And from there, we're trying to derive constraints on dark matter and dark energy. So a way to use machine learning and AI in this process is, for example, in the technical way in which we measure distances of galaxies. This, I don't know how aware are you, but one of the biggest and most interesting challenges that we keep having as astronomers is that we need to measure distances to things. And so we can use machine learning. It's actually being used, machine learning is used today to derive distances to these galaxies from different images. And from that, extract the structure of the universe. Another way is through these simulations, from emulating this type of simulations, while exploring different choices of physics and dark matter and dark energy, we can use these simulated universes to compare to the real universe and say something interesting about dark matter and dark energy. So it's mostly I would say the traditional neural networks and the deep, the traditional machine learning and the deep neural networks that are utilized today to address these questions. But I expect more data science techniques to be used in the future.
Great, yeah. And in the interest of time, we'll probably just take two more questions in person over there. Oh, sorry, behind you. Great. Okay. So the question was when you talked about citizen science, right? So for those projects, how are you ensure that the citizen scientists, they are interpreting the data and labeling the data in the correct way so that it's not really creating any like fault or incorrect results later? So perhaps like a really quick answer.
Yes, that's an excellent question. So first of all, the answer is trial and error. You sort of start and then you see if there are different types of errors that arise in the data from the classifications that you're getting. You're understanding it's not that the citizen scientists were wrong, as that you haven't really guided them enough in the process of classification. And so this process gets better and better with time. We have different learned experiences of how to do it properly. More specifically, obviously, there will be a spread in the answers that people will give. We're trying to give very specific questions about galaxies. How many spiral arms that are you seeing? How many centers are you seeing? And we're giving examples of what do we define, for example, as bars. But even then, you will have a spread in the type of answers that you're going to get for a classification. And what we usually do, we make a decision from all of the different votes that we have. This process is not exactly democratic. Some users are identified as users whose answer correlates more well with the real answer, whereas other users, their answer correlates less well. And so there is some weighting that is done. An interesting thing is that you can also check what is the accuracy in the classification as a function of the time of the day. And there are peaks where the accuracy of humans actually decreases a bit. So for example, one time is after lunch, where people are digesting, they are sort of, so they don't want to get back to work, so they classify galaxies instead, and they perhaps pay a bit less attention to how to do it. Another one is as you move further into the night. So all of these things are things that we can sort of see when we have enough classifiers to make this process, and then we know how to weigh all of these different decisions together. But we're doing some sort of voting where we also explore as scientists the outputs to make sure that nothing went extremely wrong. So for example, in one of the first examples of the Zooniverse, where they classified galaxy images, it turned out that from the classification, it seems like galaxies have a preference to rotate to one side compared to another side. And it turned out that this was just because the images we provided for the scientists, if we had flipped them and gave them flipped versions as well, this bias would have gone away. So these things we learn after we sort of have the citizen scientists classify everything, find that galaxies for some reason rotate only to one side and not to the other, and then try to understand what happened and fix it.
Yeah, and there's a related question from an online audience member asking, so aside from citizen science for classification, do you ever use AI to create the training sets?
That's a very interesting question, and thank you very much for it, because for some reason I haven't mentioned it in the talk. Another way to create training samples is actually by using simulation. So we can use these large-scale simulations to provide us with examples of astronomical observations. We need to sort of go from the simulations to the process of observing. So for example, in simulations like the cosmological simulations I showed you before, we actually simulate galaxies. And so we can employ certain predictions about how the structure of the galaxies is going to be seen in images. So we need to sort of understand what type of radiation the stars in the galaxy emit, what this radiation has to pass through as the light comes to our telescope, through the atmosphere, through the entire universe, what our instrument does to the observations. And then we can sort of create mock images of galaxies, and then we can train using these mock images. These things are being done within astronomy, especially in cases where training data is hard to get. So one such example is, or at least used to be, strong gravitational lenses, where Einstein's theory of general relativity predicts that light from galaxies bends due to concentrated regions of mass in space. And this bending creates different types of distortions that we see as rings or multiply imaged galaxies in the same region. And these events are extremely rare. So it's very difficult to build large samples where you have these labels of strong gravitational lenses to train the models on. And so you can simulate these types of events using some definition of what light goes through in our telescope and instrument. The challenge with the simulations part is that these neural networks are so powerful and so flexible that they learn every aspect of the data. And so in many cases, when we train these models on simulated data, they actually perform quite poorly on real data because it's not the same thing. We are not yet able to simulate astronomical observations well enough to be able to do that. And then there is an entire field that is called domain adaptation, where you're training your network on simulated data, and then you adapt it to real data, and then you need much less data. You fine-tune the model after it has been trained on simulation. You fine-tune it with a sprinkle of real observations. So that's another ongoing research field within astronomy.
Great. Thank you very much. Okay, so one last question from you, yeah.
But that would take a lot of computer power, energy. And I was wondering if maybe using quantum computer or some sort of similar computing technique would make this
Fantastic question. So the question was, since it requires a lot of computing power to actually run all those cosmological simulations that has a lot of physics, have you ever considered using like quantum computers to make it more efficient and perhaps that's also more environmentally friendly?
Yes, that's an excellent question. Thank you very much for asking it. I think that at some point there were discussions about trying to think whether these types of simulations can be done using quantum computing. And at least this is the knowledge that I have from, I don't know, 7, maybe 10 years ago. I think that then the answer that they reached is that the type of problems that quantum computing can solve is not the type where we're calculating how gravity and hydrodynamics change the structure of the system. I think because of the fact that you need to take into account things that can take place over large distances, forces that affect particles from very distant places. But I can recheck it and let you know, because this is a very old knowledge that I have about it, and I want to make sure maybe people have changed their minds about that since then.
Great. All right, so let's give Dalya another round of applause. So before we wrap up the event, I wanted to just take 2 minutes, I'm very well aware of the time, to quickly introduce what's coming up. So the first event, as we're continuing our programming in 2025, is a public stargazing at the Student Observatory at Stanford. So all of you might already know weather hasn't been cooperating. So we're really hoping to try to schedule an event either later this month or in early March. And we will announce that as soon as we have the date. And we'll announce it just through our mailing list as well as our event page. And also on April the 19th, that's a Saturday, there will be a science fair, also led by KIPAC, on the Stanford campus. So there will be numerous hands-on activities, live demonstrations, and experiments. There are also a series of mini science lectures, not only about astrophysics, but also from a wide variety of STEM fields, and talking about how we can apply different STEM disciplines also in space-related discoveries and studies. And if you feel bored between now and April, just cannot wait to get to another lecture, there is an annual Bunyan lecture not hosted by us, but hosted by the physics department here at Stanford, where they will have a Nobel laureate speaker talking about the expansion history of the universe, and especially how we can use the James Webb Space Telescope to reconcile some of the inconsistent measurements of the expansion rate of the universe. So if you would like to keep up with what's new with us, or simply just get notified when there's an event being planned, we welcome you to follow our social media and also sign up for the mailing list. So thank you everyone for joining us tonight. Let's bring everyone back to the screen to say goodbye. So tomorrow we will follow up with an email also asking for feedback. So what you liked about this lecture, what you didn't, and what other topics that you would like to hear in future lectures. So thanks again, everybody, and have a good night.